Space has no off switch for radiation. Even meter-thick walls can backfire by spawning secondary particles that hit you from inside the shield. In the next minutes, I'll show why zero risk is impossible in space, why water helps but never to absolute safety, and how real crews actually stack the odds in their favor. If you want a clean, hype-free answer to what truly works and why the perfect shield doesn't, stay with me, because the payoff is a simple, usable plan you can remember. Here's the plan for this episode. First, we'll map the radiation you meet beyond Earth, ever-present galactic cosmic rays, sudden solar particle storms, and the secondary radiation your own habitat can create. Then, we'll test the common myths, like just add more metal, and show where thickness helps and where it makes things worse. We'll stress test active ideas such as magnetic or plasma shields and explain why they can deflect some charged particles yet leave dangerous gaps. After that, we'll build a practical layer cake using hydrogen-rich materials, water and supplies arranged as shielding, compact storm shelters, and smart interior layouts. We'll add operational tactics, choosing safer routes and launch windows, monitoring dose in real time, and switching to storm protocols during solar events. On surfaces like the Moon or Mars, we'll use local soil to bury habitats and compare how protection strategies change when there's no global magnetic field. Along the way, I'll flag quick wins and honest limits. By the end, you'll get a clear checklist for flight and surface missions: what to carry, how to arrange it, when to hide, and what not to waste mass on. The goal isn't a fantasy bubble with zero radiation. It's a realistic, combined strategy that cuts risk to something humans can actually live with. We cannot build a good defense until we name the attacker. Cosmic radiation is not one thing. It is a moving crowd with different energies, charges, and ways to injure living tissue. This chapter draws a simple, practical map of that crowd, so every later choice, materials, layout, timing, and crew behavior, has a clear target. Beyond Earth, you meet four families. Galactic cosmic rays form a steady background of extremely energetic particles arriving from outside our solar system. Solar particle events are sudden bursts of mostly protons ejected by the sun during flares and coronal mass ejections. Trapped radiation belts near some planets, like Earth's Van Allen belts, hold particles spiraling along magnetic field lines. And inside your own vehicle or habitat, high-energy primaries can create a hidden fourth threat: secondary radiation produced when those primaries smash into your shielding, tanks, and structural materials. Most dangerous cosmic rays are not rays at all, they are particles. The chief players are protons and heavier atomic nuclei moving at a significant fraction of light speed. Heavy, high-energy ions, iron nuclei are a classic example, are sometimes called HCE particles. A single HCE ion can cut a dense, needle-like track through tissue and deposit a large amount of energy along that line, which is harder for cells to repair cleanly. Two physical qualities drive the risk: energy and electric charge. High energy makes a particle difficult to stop. High charge makes it interact strongly with matter and dump more energy per millimeter as it passes. That dump is called linear energy transfer, or LET. Low LET radiation, like common medical X-rays, tends to spread damage more diffusely. High LET particles carve narrow, intense streaks that raise the odds of complex DNA damage and misrepair. Even a small number of these big hitters can matter. Dose is the next anchor. Think of total dose as the amount of energy delivered to your body over time, and dose rate as how fast it arrives. Both change risk. A slow trickle from galactic cosmic rays accumulates during long missions. A sudden surge during a solar particle event can push you into dangerous territory within hours if you are not in a shelter. The same total amount of radiation delivered in 10 minutes is not equal in biological effect to the same amount spread over 10 months. Dose rate shapes the outcome. Environment reshapes the threat. low Earth orbit still benefits from partial protection by Earth's magnetic field and from the atmosphere below. Move to cislunar space and that protection drops sharply. On the Moon there is no global magnetic field and almost no atmosphere. Space weather arrives more directly. Mars offers a thin atmosphere and patchy crustal magnetism. Some help, but far less than Earth. Even inside one vehicle, the picture changes with where you sleep and work. A well-placed water tank, food stores, or waste containers can cast a protective shadow over crew quarters and lower personal dose. A single relativistic iron nucleus can slice through thousands of cells in a straight line, leaving a dense cluster of hits along one track. The body has repair systems, but cluster damage is harder to fix without errors. This contributes to conservative risk models for deep space travel and is a key reason perfect safety is not a realistic goal. Time adds structure. The galactic background is always on, but it breathes with the solar cycle. During solar maximum, stronger solar magnetic activity can partially suppress galactic cosmic rays. During solar minimum, that background rises. Solar particle events are episodic, quiet stretches punctuated by spikes. You cannot predict the exact event far in advance, but you can design around the statistics. Practically, missions need 2 levels of defense, an everyday baseline for the constant drizzle, and a storm mode you activate when the sun launches a proton storm. Secondary radiation is the most counterintuitive part. A high-energy particle does not simply stop like a bullet in a block of metal. When it collides with atoms in your shield, it can break their nuclei and create showers of new particles, neutrons, lighter ions, and photons. Some of those secondaries are more biologically damaging per unit of energy than the original particle. If your shield is made of dense, high-Z metal, you may reduce some primaries yet increase harmful secondaries deeper inside the habitat. Material choice and layering change not only how many primaries get through, but also what kind of secondaries you manufacture. Now, connect the physics to the body. Radiation damages DNA directly and through reactive molecules formed along the track. Cells can repair much of this damage, but probability accumulates over time. With long missions and high-lead tracks, the chance of misrepair rises. Stochastic effects like cancer do not flip from 0 to 1 at a neat threshold. Risk increases with dose and with the quality of that dose. The practical goal is not fantasy zero. The goal is to push the probability curve down by lowering the number and intensity of damaging tracks, by shortening exposure to spikes, and by placing the right materials in the right places. Individual variability matters. People differ in baseline risk, repair efficiency, and sensitivity. Screening, personal dosimetry, and conservative limits help manage that variability. Medical countermeasures may add modest protection, but there is no pill that erases high T damage. The backbone of protection remains smart shielding and smart operations. Keep a simple map in mind. 4 threat families: the steady galactic background, the spiky solar storms, trapped belts near some planets, and the secondaries born in your own hardware. 4 control levers: materials, geometry, behavior, and timing. Materials decide how particles slow down and what secondaries appear. Geometry, how you place water, food, fuel, and equipment, creates protective shadows where crews spend the most time. Behavior, when you work outside, where you stand during tasks, and how fast you respond to alerts, shifts dose dramatically without adding mass. Timing, launch windows, cruise trajectories, and awareness of the solar cycle moves the whole risk envelope before you even build the ship. Hydrogen-rich materials such as water and certain polymers are often better at soaking up charged particles while producing fewer high-energy secondaries. Compact storm shelters with high surface density can turn a lethal solar event into a survivable interruption. On the surface of the Moon or Mars, burying habitats under local soil buys substantial protection without launching that mass from Earth. Real-time dose monitoring closes the loop so crews can adjust behavior before small problems become big ones. The most common instinct is simple: make the walls thicker. If particles are bullets, more wall should mean more safety. In space, that instinct fails in surprising ways. Thickness helps against some parts of the spectrum and hurts against others, and past a certain point, it can even manufacture a new problem inside your own habitat. Here is why. A high-energy charge particle does not stop like a slow bullet sinking into clay. When it hits an atom in your shield, it can shatter that atom's nucleus and throw off a small storm of fragments. This breakup is called nuclear spallation. The fragments include lighter ions, gamma rays, and, very importantly, neutrons. Neutrons do not care about electric fields. They sail through many materials that would have deflected or slowed a charged particle. The net effect is that a thick, dense wall can reduce some primaries, but flood the interior with secondaries that are biologically efficient at causing damage. In other words, you traded one kind of trouble for another. Material choice decides how bad that trade is.
Dense, high-Z metals like lead are terrific at stopping photons, but they are exactly the sort of targets that turn a fast, heavy ion into a spray of secondaries. Hydrogen-rich materials, such as water and certain polymers, tend to slow protons and many heavy ions more gently and produce fewer high-energy secondaries. Hydrogen is light, so an incoming particle scatters many times and loses energy without as many violent nuclear breakups. This is the heart of modern passive shielding, not just thickness, but the chemistry of the thickness. Another subtlety is energy. The spectrum of space radiation stretches from modest energies common in solar particle events to extremely high energies typical of galactic cosmic rays. A layer that is excellent against a solar proton storm might be far less effective against the hardest, highest energy ions from deep space. You can easily build enough aerial density to tame a typical solar event. Think in terms of many centimeters of water or polymer around a compact shelter, but building enough to tame the full GCR spectrum would demand impractical mass for a crude vehicle. At some thickness, returns diminish and the secondary field grows. That is the too thick in the wrong stuff trap. Geometry matters as much as the bill of materials. Cosmic radiation does not arrive as a neat beam from one direction. It comes from almost everywhere, and its exact distribution depends on your location and the current solar conditions. A uniform shell wastes mass where it buys little protection and may be too thin where you need it most. A smarter approach is to put mass where people spend the most time and where the worst flux comes from. Tanks, food, water recyclers, waste containers, spare parts, these are valuable not only for their function, but also as movable bricks of hydrogen-rich matter. Arrange them around sleeping quarters and workstations to cast protective shadows. Instead of chasing a perfect cocoon, you reshape the interior so the crew's bodies live behind the thickest, most helpful stuff most of the day. There is also the question of path length through curved walls. A thin cylinder gives very different protection depending on angle. At a shallow grazing angle, a particle may traverse a long diagonal path. At a normal angle, only a thin section. Rounded shapes like spheres and tori help smooth those extremes, but are not always practical for launch, docking, or internal layout. The engineering reality is compromise. You blend structural efficiency, launch constraints, and interior ergonomics, then backfill with smart placement of consumables to fix the weak spots. Mass is not a footnote, it is the central budget. Every kilogram you add to shielding is a kilogram you do not carry as science equipment, fuel, life support margins, or spare parts. In deep space missions, that trade is brutal. A thick global shell that meaningfully suppresses the highest energy ions might cost tens of tons for a small habitat. That mass also needs structure to hold it, propulsion to move it, and thermal control to manage the heat it absorbs. Overbuild the shield and you can quietly make the rest of the mission impossible. Thermal and structural side effects add friction. A thick, dense layer absorbs energy and re-radiates it as heat. Your cooling system needs to move that heat somewhere, which costs power and complexity. Some shielding materials outgas in vacuum or degrade under radiation, becoming brittle or shedding particles that contaminate optics and mechanisms. Adhesives and foams that look great on paper can age poorly under combined radiation, vacuum, and temperature cycling. Protection that fails halfway to Mars is not protection. It is dead weight that creates new failure modes. There is an additional trap in thinking of thickness as a uniform number, like 10 centimeters of X everywhere. Not all centimeters are equal. 10 centimeters of aluminum, 10 centimeters of polyethylene, and 10 centimeters of water have very different effects on different parts of the spectrum. Engineers compare shields using areal density, often measured in grams per square centimeter, and even that is only a first approximation. What counts is how that mass is distributed by element and by layer. Graded Z shields, stacking materials from low atomic number to higher or alternating layers, can steer the cascade of secondaries into less harmful channels. The principle is to let the first layers take the brunt and slow primaries gently, and then let following layers mop up what remains, rather than creating a big spallation burst right next to the crew. Solar storms deserve their own note. During a major event, the particle energies, though high, are typically lower than the top end of the galactic spectrum. That is good news. A compact shelter encased by tanks and supplies can slash the dose dramatically, and it is feasible to build such storm rooms even on mass-constrained missions. The bad news is timing and behavior. If the crew is outside or far from the shelter when an event begins, minutes matter. A design that relies on thickness alone will disappoint you if it is not paired with fast alerts, clear procedures, and a layout that lets people reach refuge quickly. On planetary surfaces, the thicker is better idea gets a second life, but with local materials. Regolith, loose soil and rock, can be piled or printed over habitats to add substantial aerial density without launching it from Earth. This is where thickness becomes your friend again, because hauling mass is no longer the limiting factor. Even here, composition still matters. Lunar and Martian soils are not hydrogen-rich. They are mixtures of heavier elements that can create secondaries. The trick is to combine local soil outside with hydrogen-rich liners inside, so the outer layer slows and spreads the spectrum, and the inner layer cleans up the cascade before it reaches people. Bremsstrahlung, radiation emitted when charged particles are decelerated, adds another wrinkle. Dense metals produce more of it when fast electrons are involved. If your shield's job includes stopping electrons and gamma rays from a particular environment, metal has advantages. But if you are stopping heavy ions, that same metal can increase the photon component you then have to absorb with yet more material. This is another reason layered designs beat single material slabs. Testing the just thicker idea must also include survivability and maintenance. A perfect shield that cannot be inspected, repaired, or reconfigured as consumables are used up is not perfect for long. Water tanks empty, food is eaten, waste volume grows, and mission phases change. A design that expects fixed thickness everywhere ignores the moving geometry of a long flight. The practical approach is modular. Shields that double as tanks, storage that migrates to maintain protection where people sleep, and a storm shelter whose mass stays high even as you consume supplies. The psychological dimension is real. If the crew believes that thick equals safe, They may take unnecessary risks during solar quiet days and underestimate galactic exposure building up in the background. In training and in procedures, the message has to be clear. Thickness is a tool, not a guarantee. The numbers you carry on a dosimeter, the alerts you receive from space weather forecasts, and the discipline to use the shelter on short notice are equally important parts of the same system. In summary, for this chapter's idea in plain language, thickness helps, but only if it is the right kind of thickness, in the right place, and paired with the right operations.
Dense metals are not universal shields. They can create more dangerous byproducts. Hydrogen-rich materials soften the blow but cannot erase the hardest cosmic ions. A uniform cocoon wastes mass and leaves gaps. A thoughtful interior with layered materials, consumables as walls, and a ready storm shelter makes the same mass work much harder. And none of it works well without fast alerts, smart timing, and disciplined behavior. The dream is simple. Bend radiation away with invisible force fields. If charged particles respond to electric and magnetic forces, why not surround a ship with a bubble that steers them aside? The physics does allow deflection, but the practical requirements make full protection far harder than it sounds. Start with magnets. A moving charged particle curves in a magnetic field. The stronger the field and the lower the particle's momentum, the tighter the curve. High-energy space particles, especially the heavy ions in galactic cosmic rays, carry so much momentum that they hardly bend near a spacecraft. Even multi-Tesla fields close to the hull only nudge them a little. To give those particles enough time and distance to arc away, you would need either an enormous magnetic volume extending far from the ship or field strengths and structures that are extremely difficult to build, power, cool, and keep stable in flight. Superconducting coils are the obvious path to strong fields without waste heat from resistance. But superconductors introduce their own burdens. They must be kept cold, which means cryocoolers, radiators, and insulation. They must survive launch loads, micrometeoroids, and years of radiation without degrading. They store large amounts of magnetic energy, so a sudden loss of superconductivity, called a quench, can dump that energy as heat and stress into the structure. The coils also pull on themselves with huge forces. The mechanical support becomes heavy. Each kilogram you devote to magnets and cryogenics is a kilogram not invested in life support, fuel, or science. Field shape matters. A simple solenoid can generate a strong field, but it also fills the living space with magnetic flux. That can interfere with instruments, induce currents in wiring, and create strict keep-out zones for tools and devices with ferromagnetic parts. Toroidal coils can confine most of the field away from the interior, but they are complex, heavy structures that must encircle the habitat. Real designs fight a three-way trade: strong external field to deflect particles, minimal internal field for crew and electronics, and a structure that can be launched and assembled without breaking. A tension point. A magnetic shield does not touch neutral particles or photons. Neutrons, X-rays, and gamma rays ignore magnetic forces. Even perfect magnetic geometry would still leave you exposed to those components. For that reason alone, active systems cannot be the whole answer. Now consider electrostatic shielding. The idea is to charge the ship to a high voltage, so charged particles are repelled or attracted away. In practice, space plasma quickly cancels those charges. Ambient electrons and ions flow to your vehicle and neutralize the potential. To maintain a strong electric field, you would need to continuously emit or collect charge and hold differences of hundreds of kilovolts to megavolts across large distances. High voltages in vacuum bring arcing, field emission, and sharp-edge hotspots that can damage surfaces and generate unwanted X-rays when accelerated electrons slam into the hull. The equipment becomes a reliability risk, and the fields still do nothing to neutral radiation.
a hybrid concept tries to enlarge a small magnetic field by filling it with plasma, creating a miniature magnetosphere. Injected plasma can inflate field lines and push the solar wind back a short distance, forming a standoff region in front of the vehicle.
Laboratory and small-scale tests suggest such bubbles can deflect a fraction of incoming charged particles, especially at the lower energies typical of solar wind and some solar particle events. But turning that effect into a reliable, crew-scale shield is tricky. You need a steady plasma source, power to sustain it, and control systems to keep the bubble stable when the solar wind changes. The standoff distance, the space between the ship and the boundary where particles are diverted, must be large enough that bent trajectories miss the hull. That tends to demand more field, more plasma, and more power, all while handling unpredictable space weather. Active ideas also introduce side effects that mission designers cannot ignore. Strong fields couple to the space environment and can generate torques on the spacecraft as they interact with the interplanetary magnetic field. That complicates attitude control and may require continuous counter-torques from reaction wheels or thrusters. Magnetic fields can trap some particles locally, creating cusps or pockets where flux concentrates. Sensitive instruments, especially magnetometers, mass spectrometers, and imaging devices, may need to sit far from coils, costing you valuable real estate. Electrostatic structures invite surface charging and discharges that pit coatings and contaminate optics. Let's return to the part of the spectrum where active defenses help most: solar particle events. During a major event, the dominant hazard is a flood of protons with energies that, while high, are lower than the top end of the galactic cosmic ray spectrum. Deflecting a portion of that proton flux can cut dose significantly, and the benefit stacks with passive protection. The catch is timing and reliability. Solar events can rise quickly. If your active system fails to start, or if it only protects a narrow cone in front, while particles arrive from many directions, the crew still needs a passive storm shelter ready to use. In other words, an active layer is an enhancer, not a replacement. Attention point: active systems do not create nuclear spallation cascades the way dense passive shields can, because they avoid direct collisions with heavy material. That is a real advantage. But the price you pay is complexity, power draw, thermal management, control stability, and the fact that neutral and very high energy components sail straight through no matter how clever the fields are. There is also the matter of scale. To double the deflection of a high energy ion, you can double the magnetic field or double the distance over which the field acts. The first option drives coil and cryogenic demands up fast. The second option demands a field that extends many meters, sometimes tens or hundreds of meters, around the vehicle. Deployable booms or inflatable structures could, in theory, hold coils at a standoff distance, but then micrometeoroids, vibrations, thermal cycles, and docking operations all become harder problems. Every design choice echoes through the rest of the spacecraft. Health and human factors cannot be ignored. Persistent magnetic fields in living spaces must stay within conservative limits for crew safety and for medical devices. Tools, exercise equipment, and small steel parts behave strangely near strong fields. Electrostatic systems can elevate ozone and nitrogen oxides in tiny amounts if discharges occur, adding another environmental control load. If a system fails, it should fail safe. No uncontrolled arcing, no sudden coil quenches that heat the cabin, no plasma plume pointed at a sensitive sensor. Power is a hard constraint. Deep space missions run on limited generation capacity, whether from solar arrays that weaken with distance from the sun or from radioisotope systems sized for life support and science. Allocating kilowatts to pumps, cryocoolers, plasma sources, and control loops is not free. That power comes from somewhere: battery mass, bigger arrays, or a cut to other mission goals. With all of that said, active methods still have a place. They can be targeted to protect specific high-value areas,
like external instruments, electronics bays, or airlocks during short tasks. They can reduce the lower energy tail of incoming spectra so that the passive layers behind them work less hard. They can help manage spacecraft charging and surface potentials, which indirectly lowers risk. And research into compact superconductors, better cryocoolers, and more stable plasma configurations continues to improve what is practical. The sober bottom line is this: active shields can meaningfully reduce part of the threat, especially for charged particles at lower energies typical of solar activity. They are far less effective against the heaviest, highest energy ions that dominate long-duration deep space risk, and they do nothing for neutral and photon radiation. They add mass, power, complexity, and new failure modes that must be managed. In any realistic mission, they act as a supplement to passive, hydrogen-rich materials and to smart operations, not as a magic bubble that replaces them. For crews and designers, the takeaway is to treat active systems as one layer in a combined approach. Use them where they buy the most benefit per kilogram and per watt. Keep living spaces quiet and safe from stray fields, budget for cryogenics and control, or choose concepts that avoid those needs, and never bet the mission on a single technology that claims to turn the cosmos off. There is no off switch, only smarter ways to push the odds in your favor. Biology sets the hardest limits because human tissue cannot be redesigned between launch and landing. Radiation damage begins at the molecular scale and scales up to tissues, organs, and behavior. At the DNA level, charged particles create breaks, crosslinks, and clusters of lesions packed tightly along their tracks.
Highlight particles, especially heavy ions, lay down dense, complex damage that cells find difficult to repair without errors. Misrepairs can become mutations, and the risk accumulates over time rather than switching on at a neat threshold. Two categories help make sense of outcomes. Deterministic effects have thresholds. Exceed enough dose over a short time and you see predictable tissue reactions, from skin erythema to bone marrow suppression. Stochastic effects are probabilistic. The chance of cancer or certain degenerative diseases rises with dose, even when no immediate symptoms appear. Space travel mixes both. A large, fast solar particle event without shelter can drive toward deterministic territory in hours. The everyday drizzle of galactic cosmic rays works in the stochastic domain, pushing long-term risk upward through countless small hits. Dose rate changes the story. The same total energy delivered in 10 minutes is not biologically equal to the same amount spread across 10 months. Rapid delivery overwhelms repair pathways and inflames tissues. Slow delivery gives cells time to respond, but it also allows many opportunities for misrepair to slip through. That is why mission procedures aim to avoid spikes while patiently chipping away at the background with shielding, smart layout, and time management. Different organs carry different vulnerabilities. Bone marrow is sensitive because it continuously produces blood cells. Sustained exposure can blunt immune function, and anemia can appear as the body turns over red blood cells. The lens of the eye is vulnerable to opacities. Even moderate cumulative exposure can nudge cataract risk upward sooner than expected. The cardiovascular system responds to chronic inflammation and endothelial damage. Long missions raise questions about accelerated atherosclerotic change. The central nervous system is a special concern with high lead particles. Animal studies show cognitive and behavioral changes after realistic heavy ion exposures, pointing to oxidative stress, neuroinflammation, and damage to dendrites and synapses. Translating those findings to humans remains an active area of research, but they push planners to be conservative for deep space durations. Biology never happens in a vacuum. Microgravity, elevated carbon dioxide, disrupted sleep, isolation, and dust exposure all interact with radiation. Microgravity shifts fluids toward the head, alters immune responses, and weakens bones and muscles.
Elevated CO2 can worsen headaches and fatigue. Poor sleep and circadian drift impair repair and decision-making, making it harder to execute protective routines during a solar event. None of these stresses are lethal alone, but together they squeeze margins. A workable plan treats radiation as part of a combined environmental load, not as a separate silo. Individual variability matters. Age, sex, prior medical history, and genetic differences in DNA repair and antioxidant systems change baseline risk. 2 crew members can receive the same physical dose, but not the same biological impact. That is why crews carry personal dosimeters, why mission limits are set per person, and why agencies use conservative models with uncertainty buffers rather than a single perfect number. In practice, acceptable lifetime risk is allocated across missions, and each mission carves its slice carefully. Quality of radiation matters as much as quantity. Equivalent dose uses a weighting factor to reflect the higher biological punch of high Li-T tracks compared to low Li-T photons. But those weightings are simplifications. Real tissues see a spectrum, and the spectrum changes with shielding. A wall that lowers the number of high-energy ions but increases a spray of neutrons and lower-energy fragments can shift biological effectiveness in unexpected ways. Good design tries to soften the spectrum, less high Li-T, fewer energetic secondaries, before it reaches people. Acute radiation syndrome is a real possibility in worst-case solar storms if a crew is unprotected on EVA or far from shelter. Early symptoms mimic many other stresses, nausea, fatigue, skin changes, and can be easy to misread during a busy operation. The immediate defense is architectural and behavioral rather than pharmaceutical. Real-time alerts, clear drop everything and shelter procedures, and a storm room close enough that no one wastes minutes getting there. Inside that shelter, thick hydrogen-rich mass slows the proton flood and buys time. With that setup, events that could be dangerous outside become survivable interruptions inside. Medical countermeasures are a supporting cast, not the lead actor. Antioxidants and radioprotective candidates are understudy, but no pill cancels the core problem of clustered high Li-T damage. What does help is building physiological resilience, strong baseline fitness, disciplined sleep hygiene, CO2 control, nutrition that supports repair pathways, and steady exercise to preserve bone and muscle. These do not block tracks. They improve recovery and performance so crews can execute the protective behaviors that truly move the needle. Monitoring is the nervous system of protection. Passive dosimeters record accumulated dose. Active instruments show dose rate in real time and alert crews when the spectrum shifts. Organ-equivalent dosimetry, estimating doses to lens, marrow, skin, and brain, guides where to place mass and how to rotate tasks. If one area of the habitat runs hot due to geometry, sleep stations move, tanks shift, or extra panels go up. Data flows into decisions every day rather than only into post-mission reports. Behavioral tactics pay off with no launch cost. Limit time in areas with high flux, especially near thin sections of hull.
Schedule EVAs when solar conditions are quiet. Keep suits and rovers staged so a retreat to shelter is fast. Spread high-dose tasks across crew members to avoid burdening a single person's lifetime risk. Treat the storm shelter like a seatbelt, uncomfortable to think about, routine to use. On planetary surfaces, biology meets geology. Local soil piled over habitats increases aerial density and lowers dose, protecting marrow, lens, and brain during rest, the long hours when the body does most of its repair. Hydrogen-rich liners beneath that soil reduce harmful secondaries. Daily operations still matter. Dust control, good ventilation, and conservative EVA plans keep mucosal tissues and lungs healthier, which indirectly strengthens resilience to radiation stress. Uncertainty is part of the current state of knowledge. Ground experiments use accelerators to simulate space radiation, but they cannot perfectly reproduce the mixed chronic field of deep space. Translating animal outcomes to human risk carries error bars. That uncertainty does not paralyze planning, it argues for margin. Designs that push dose lower, especially high-let components, buy safety against both known risks and the error bars around them. Psychology matters because perception shapes behavior. If crews believe the habitat is a perfect cocoon, they may underuse the shelter or ignore rising dose rates. If they feel helpless, they may freeze when speed matters. The right mindset is practical and specific. Radiation is a managed hazard. We watch the numbers. We move to shelter on signal. We place mass where we sleep. We keep EVAs short during active solar periods. Confidence comes from drills, not from slogans. In plain terms, the human body can tolerate a lot when given time, rest, and smart routines, but it cannot negotiate with highly T tracks. The path forward is to reduce how many of those tracks reach sensitive tissues, to avoid bursts that overwhelm repair, and to support the body so it does its work between hits. That is why the core of protection remains the same. Hydrogen-rich materials close to people, consumables arranged as shields, compact storm shelters for spikes, careful scheduling, and continuous awareness of dose. Biology sets the ceiling, engineering and operations make sure we never hit it. Materials are not just a wall, they are a spectrum shaper. The goal is to slow and soften incoming particles while avoiding a spray of harmful secondaries. That is why hydrogen-rich matter sits at the center of practical shielding. Hydrogen gives many small, gentle collisions instead of a few violent nuclear breakups. Water is the most obvious candidate because it already rides along for life support. Polyethylene and other hydrogen-rich polymers are close behind. When a proton or heavy ion plows into these materials, it loses energy in many steps and exits less dangerous, or stops entirely without producing as many high-energy neutrons as dense metals do. Water earns its seat twice. It is mass you must carry anyway, and it can be placed where it does the most good. Lining crew quarters with water bags, routing potable and grey water tanks around sleeping stations, and building wet walls around high-occupancy areas can cut dose without adding dedicated ballast. Even waste streams become useful. Urine and brine tanks have high hydrogen content and can be stacked into panels that double as shielding. Food is also a quiet ally. Dehydrated goods are light, but many packaged foods contain water or oils. Stored smartly, pallets of rations become movable bricks of protection that can be rotated as they are consumed. Hydrogen-rich polymers bring structure where water is awkward. Ultra-high molecular weight polyethylene can be molded into panels, liners, and lockers that survive launch loads and daily wear. It machines cleanly, does not need plumbing, and does not slosh. Composite laminates that sandwich polyethylene between stiffer faces turn into floors, bunks, and cabinet walls that pay for themselves twice. They do their everyday job and take the edge off radiation in the background. Where neutron control matters, boron-loaded polymers add another lever. Boron-10 captures thermal neutrons and converts them into short-range charged particles that stop locally, reducing the neutron component that otherwise sneaks through many materials. Layering beats single material slabs. A graded approach uses low Z materials upfront to slow primaries and minimize spallation, then adds targeted layers to mop up what remains. Hydrogen-rich panels face the outside to drain energy from protons and heavy ions. Behind them, a thin boron-loaded layer trims neutrons that were born in the slowing process. If you expect a photon tail, bremsstrahlung from fast electrons or capture gammas from certain interactions, a modest layer of medium Z material can help absorb those photons, provided it is not thick enough to create new showers. The exact stack depends on your route, mission duration, and the spectra you expect, but the principle stays the same. Slow gently,
absorb selectively, avoid violent nuclear breakups near people. Geometry makes the same kilograms work harder. A uniform shell wastes mass in directions and locations that crew rarely occupy. Concentrate aerial density where bodies actually spend time. Surround sleep stations, galley seating, and work consoles with hydrogen-rich mass. Build storage into thickened ceilings and walls around those zones. Keep thinner paths for corridors and low-occupancy equipment bays. The number that quietly drives these choices is aerial density, measured in grams per square centimeter.
For storm shelters aimed at solar particle events, stacking consumables and water to reach on the order of a dozen or more grams per square centimeter around a compact volume can slash dose rates dramatically during a flare, while the rest of the habitat remains lighter for everyday use. A storm shelter succeeds or fails on details. It must be close enough that no one wastes minutes reaching it. It must be sized for the entire crew, with room to sit, breathe, and work for hours. Its walls should be thickest where heads and torsos rest, not just where it is easy to mount bags. Tanks and food should be strapped so they do not shift when bumped. Lighting, fans, and CO2 scrubbing must be comfortable enough that people actually use the shelter without hesitation. If the experience is unpleasant, crews will delay moving during a real event, and dose accumulates when seconds matter. Consumables change over time. Your shield should change with them. As water is drunk and food is eaten, the geometry of protection tends to erode in the very places where people sleep and work. Plan a mass management schedule that keeps protection balanced. Move full tanks forward as others empty. Repackage waste into standardized containers that can take the place of spent food pallets. Use modular racks with quick latches so mass can be rearranged during routine housekeeping, not only during emergency drills. Treat "Where is our hydrogen today?" as a checklist item on weekly timelines. Cryogenic propellants look attractive on paper. Liquid hydrogen is the ultimate hydrogen-rich material, but cryosystems are unforgiving. Boil-off, insulation, and safety distances make it hard to put crew close to those tanks for long periods. Methane and other hydrocarbons are easier neighbors and still provide useful hydrogen content if their tanks can be safely integrated into walls or placed as arcs around crew spaces. If propellant must remain remote for safety and plumbing, the gap is bridged with water, polymers, and everyday stores that can live right against the habitat envelope. Not all polymers are equal. Hydrogen content per kilogram is the primary driver for slowing charged particles, but mechanical, thermal, and fire behavior matter too. Material should be low outgassing, resistant to UV and radiation-induced embrittlement, compatible with disinfectants, and safe in an oxygen-rich cabin. Additives that help with flame retardancy can reduce hydrogen fraction. This is where clever design offsets chemistry, for example by making flame-retardant skins thin and keeping the hydrogen-rich core thick. Where panels need stiffness, hybrid laminates use carbon or glass fibers sparingly, placing the hydrogen-rich core where it does the most radiological work. Bremsstrahlung and electrons complicate choices near certain environments, such as within trapped belts or around high-voltage hardware. Metals stop electrons efficiently, but produce more Bremsstrahlung. Hydrogen-rich layers produce far less of that X-ray tail. A practical layout often puts polymer first for electrons, then a thin conductive layer behind it for charge control, routing, and structural attachment, keeping metallic thickness low enough to avoid creating a photon problem bigger than the one you solved. On planetary surfaces, local soil turns thickness into a practical tool. Lunar and Martian regolith can be piled, sintered, or 3D printed over habitats to add large aerial density without launch penalties. The soil itself is not hydrogen-rich, so it is paired with inner liners of water and polymers to clean up the spectrum that leaks through. Buried habitats buy two advantages at once.
Reduce dose during long rest periods when the body does most of its repair and thermal stability that makes life support easier. Entryways and airlocks remain weak spots. Here, double-door vestibules lined with water panels and storage can shave exposure during frequent transitions in and out. Daily operations are an extension of material science. Keep high-value body parts behind hydrogen-rich mass during routine activities. Mount crew chairs so torsos face thick walls rather than windows. Place personal sleeping bags or bunks so a water tank sits between the sleeper and the thinnest hull patch. Store heavy spares and metallic tools where they help structurally, but do not sit next to heads. Metals are not villains, but they are not your first line for charged particles. When windows are essential, give them roll-down internal shutters made from flexible polymer bladders that can be filled with water for quiet periods and drained during docking or photography. Measurement keeps the plan honest. Passive dosimeters on walls and bunks show how geometry performs over weeks. Personal dosimeters show how behavior modifies dose day by day. If a zone runs hot, move mass, not people, and remeasure. Over time, the habitat learns its own best configuration. The process is not glamorous, but it is powerful. Small shifts in where you put the kilograms you already have often buy more protection than chasing exotic materials you cannot maintain. For tasks outside the vehicle, material strategy becomes clothing and tools. EVA suits cannot carry storm shelter thickness, but suit layers can include hydrogen-rich films in critical areas without bloating mass too much. Tool caddies and rover seats can integrate water or polymer blocks behind the torso. The best defense outside remains time. Do short, well-planned sorties during quiet solar periods and keep a rover or airlock within a short drive or walk. The quiet advantage of hydrogen-rich design is psychological as much as physical.
When crew can see and touch the mass that protects them, water in clear bladders, food and waste packed into tidy panels, they trust the system and use it as intended. A good design makes the safest choices, the most convenient ones. You naturally sit where the wall is thickest. You sleep where the tanks are. You spend spikes in a shelter that is comfortable enough to keep working. That is how materials turn from a static wall into a living part of the habitat, always doing quiet work between the moments when it matters most. Operations turn physics into safety. The right moves at the right time can cut radiation dose more than any single gadget. Think of the mission as a living schedule that bends around space weather, and of the habitat as a stage you rearrange to keep bodies behind mass during the hours that matter most. Start with forecasting and thresholds. Space weather is not a guess. It is a data stream that updates by the minute. Crews need a simple rule set. What counts as quiet, elevated, and storm? Quiet means normal operations with baseline shielding. Elevated means tighten exposure, shorten EVAs, move work to better shielded stations, and increase monitoring frequency. Storm means switch to the shelter protocol. These thresholds are defined before launch, drilled on the ground, and printed where everyone can see them. The moment an alert crosses a line, procedures replace debate. Dose budgeting keeps choices honest. Each mission carries a planned cumulative dose and a maximum daily dose rate. Each crew member carries a personal budget that accounts for their role and lifetime limits. A short EVA during elevated conditions might be acceptable if the week's total stays on track. A long EVA during a spike is not. Budgets are not about fear. They are about trading small amounts of risk for mission value in a controlled way. The rule is simple. If the numbers say stop, you stop. Timing is a quiet superpower. Launch during a favorable phase of the solar cycle when possible. Choose transfer trajectories that shave time in high-flux regions and avoid unnecessary loitering in trapped belts. Plan EVAs for local morning or evening when temperatures and lighting cooperate and when forecasts are quiet. If a solar region looks active, front-load interior work and shift exterior tasks to later or earlier days.
A well-timed schedule often cuts more dose than a centimeter of extra material. Attention. Minutes matter during a solar particle event. Practice the sprint. From any workstation or EVA site, crew should be able to reach the storm shelter and close the hatch within a strict time. 90 seconds is a common target on paper. That requires clear paths, no floating clutter, handholds placed for speed, and drills that make the motion automatic. On EVA, that means rover routes that always keep a quick line back to an airlock, and rovers staged with charged batteries and clean cargo areas so people can ride back immediately without reshuffling gear. Inside the habitat, layout becomes behavior. Put high occupancy tasks, meals, planning, science consoles where shields are thickest. Mount seats so torsos face hydrogen-rich panels. Store water, food, and waste where people sleep. Keep thin windows for short, intentional viewing sessions rather than a constant backdrop near bunks and desks. The goal is passive compliance. You get more protection simply by living where protection already exists. Alerts must be unmissable and unambiguous. A storm alert is a distinct tone and a single sentence. Storm mode, proceed to shelter. No jargon, no debate. The second message is timed. Shelter secured in 60 seconds. Inside, a short checklist keeps everyone busy and calm. Close valves, start fans, confirm power, confirm comms, switch non-essential systems to low power, verify dosimeter logging.
Comfort details matter. Good lighting, seating that prevents cramps, airflow that keeps CO2 pockets from forming, and basic tasks on hand so time passes productively. If the shelter is miserable, people will rationalize staying outside a little longer, and that is when dose adds up. Monitoring turns guesswork into control. Fixed sensors report dose rate by zone. Personal dosimeters ride on the torso and, when possible, near the lens of the eye. A simple display shows current rates, rolling daily totals, and a weekly bar that grows as you accumulate dose. Green, yellow, red. Crew can see their numbers in real time, and the system logs everything for trends. If one bunk or workstation runs hot, you move mass, not people, and watch the numbers drop. EVA discipline is its own craft. Pre-briefs include a weather check, a route map with safe havens, and a maximum exposure clock. Suits, tools, and spares are staged near the airlock ahead of time to avoid delays. Rover seats include polymer blocks or water bladders behind the torso. Tool caddies do the same. The plan includes a hard stop. At a set time or a set integrated dose, tasks pause and the crew returns. No sunk cost fallacy. Post-EVA, data from suit dosimeters folds into personal budgets and into planning for the week ahead. Attention. Avoid small, repeated, just 5 more minutes exposures near thin hull sections. They hide in routines, 10 minutes by a window for photos, 15 minutes near an equipment bay that faces a thin panel, 20 minutes chatting in a pretty corner. Multiply that by days and weeks and you quietly add a large fraction of the mission dose. Make the beautiful view a scheduled event in a shielded spot, not a habit. Mass management is a weekly ritual. As tanks empty and food is consumed, protection around bunks and desks can erode. Move full containers forward as others empty. Repack waste into standardized sealed bricks and place them into the slots that food pallets once occupied. Check that the shelter still meets its aerial density target after every major resupply or usage cycle. A small whiteboard sketch, updated on Sundays, shows where the mass lives this week. Communications and autonomy matter when forecasts are uncertain. If ground support is delayed, the crew still has to act. That is why thresholds, drills, and displays must stand on their own. The protocol reads the same with or without a call from Earth. The instrument crossed the line, the tone sounds, the crew moves. After the event, the debrief folds lessons into the next plan. What went smoothly, what slowed you down, which stowage choices helped or hurt. Attitude and pointing are underrated tools.
If the vehicle can rotate, you can sometimes put thicker sections between the sun and the crew during elevated conditions, especially for solar events where directionality matters. This requires coordination with thermal control and power systems. Panels, radiators, and antennas do not like sudden long holds in odd attitudes, but even modest reorientation during a spike can shave doughs. Housekeeping keeps safety fast. Clear Velcro zones for pouches and tools prevent loose items from blocking the route to shelter. Cables follow fixed paths so no one snags a foot or a tether during a sprint. Hatches open cleanly. Fans are quiet but strong enough to keep air moving in crowded spaces. Every small friction you remove in calm hours pays back when the clock is running. On planetary surfaces, operations extend the same logic. Habitats are buried or bermed so rest happens under mass. Airlocks open into short, shielded vestibules so people pass through two doors surrounded by water or polymer panels. EVA routes aim for terrain with quick cover, a rover, a shelter pod, or a bermed outpost. Dust control reduces respiratory stress so the body is better at repair during off hours. Work plans bunch exterior tasks into fewer, denser sorties on quiet days rather than many short trips across an active week. Training is the glue. Procedures only work when people can run them under stress. Drills rotate leaders so everyone can call a shelter move. Surprise no-comms drills ensure the local rules stand without help. Timed sprints from every workstation become muscle memory. The crew practices moving mass quickly, strapping extra water bags around the shelter door or sliding a storage rack to cover a thin wall, so configuration changes are smooth when needed. Power budgeting protects the core functions when it matters. Storm mode pre-allocates power to fans, CO2 scrubbing, lighting, and communications. Non-critical loads drop instantly. Batteries are kept at a healthy state of charge, so one unexpected event does not cascade into a resource crisis. Thermal control is prepared for a tighter, warmer space with many bodies. Extra airflow and a modest temperature drop prevent discomfort from turning into conflict during long holds. In plain language, operations are engineering you perform with clocks, checklists, and habits. Forecasts tell you when to move. Layout decides where your body sits while you work and sleep. Drills make shelter a reflex. Dose budgets keep ambition inside safe lines. With those tools, the same vehicle becomes far safer without adding a kilogram. Architecture is where ideals meet the rocket equation. Every kilogram you add to protection is a kilogram you cannot spend on life support, science, propellant, or margin. The design problem is not to build a bunker. It is to place the right mass in the right place for the right phase of flight, and to keep that protection effective as the mission evolves. Start with aerial density as the quiet driver. You do not need the same thickness everywhere. People sleep, eat, and work in specific zones. Put the most hydrogen-rich mass around heads and torsos where time accumulates. Let corridors, storage aisles, and infrequently used bays stay thinner. When you run the numbers, a concentrated shield around high occupancy volumes often beats a uniform shell by a large margin, with less total mass. The vehicle's shape and structure matter. Cylinders and spheres are efficient for pressure, but they give very different path lengths depending on angle. Instead of chasing geometric perfection, use layout. Wrap bunks, galley seating, and consoles with water tanks, food, and waste bricks. Build lockers and liners from hydrogen-rich polymers. Keep windows small and covered by internal roll-down polymer bladders that can be filled with water during quiet periods. Route cables and ducts so they do not block quick paths to the shelter. Mass moves during flight. Water is consumed, food is eaten, tanks empty, and others fill. Architecture should assume a moving shield and provide rails, racks, and quick latch mounts so protection follows the crew. A weekly mass map keeps the protective geometry intact. Waste is not waste. It is hydrogen-bearing ballast. Package it into sealed, standardized blocks that slide into the same slots that food once occupied. Storm shelters are small architecture projects inside the larger one. Place the shelter close to where people already are, not at the end of a maze. Size it for the full crew with enough air circulation, lighting, and seating to make hours inside tolerable. Build its walls from double-duty mass, water, brine, packaged food, and polymer panels. Put the thickest layers where heads and chests rest. Pre-wire power and comms so the room stays functional when non-critical loads drop. Active concepts fit as accessories, not foundations. If you choose localized coils or electrostatic elements, isolate them from living spaces, reserve power and cooling, and treat them as helpers against lower energy charge particles rather than as primary protection.
Keep sensitive instruments at a sensible distance and plan for failure modes that do not create new hazards. Attitude control and center of mass are not afterthoughts. When you stack tanks and stores to make a shield, the vehicle's balance shifts. Thrusters and reaction wheels feel that change. The design should tolerate moving mass without burning excessive propellant or saturating control systems. If the vehicle can safely rotate, exploit that ability during elevated solar conditions to present the thickest side toward the sun, coordinated with power, thermal, and communication needs. Thermal control and radiation control share walls. Thick, dark layers soak up heat. Radiators must reject it. Choose materials and colors that do not turn protection into a heat trap. Avoid adhesives and foams that age badly under combined radiation, vacuum, and temperature cycles. Surfaces that chalk, crack, or outgas become debris and contamination problems later. Panels should be inspectable and replaceable. A shield that cannot be maintained is not a shield for long missions. Assembly and packaging shape what is possible. Components must survive launch, fit fairings, and permit docking and maintenance. Inflatable habitats offer generous volume and invite internal polymer liners and water walls, but they demand careful routing to avoid pinch points and to maintain even shielding around key areas. Rigid modules carry panels more easily and accept heavier lockers, but their internal volume is precious. In both cases, design stowage with standard dimensions so any block of mass can become part of the shield wherever it is needed. Economics sets the boundary conditions. Mass to orbit and beyond is expensive, and every added kilogram echoes through booster choice, staging, and propellant budgets. A kilogram of well-placed hydrogen-rich polymer that protects 8 hours of sleep for years can outperform many kilograms spread thinly across the hull. Chasing exotic materials with marginal gains is rarely worth the integration cost if you can simply rearrange what you already must carry, water, food, waste, and soft furnishings, into an intelligent shield. Mission phase changes the recipe. In low Earth orbit, Earth's field helps, and trapped belts are the main hazard when changing inclinations or passing through the South Atlantic anomaly. In cislunar transit, background galactic radiation rises and solar storms matter more. A compact shelter becomes central. On lunar surface, there is no global magnetic field. Local berms and regolith overburden become practical, paired with inner hydrogen-rich liners. On Mars transit, time in deep space makes cumulative dose the driver. Sleeping zones and daily workstations need the thickest, lightest hydrogen-rich surroundings you can afford. On Mars' surface, thin atmosphere and patchy crustal fields give limited relief. Burying habitats and lining interiors with water and polymers pays off for the long nights and rest periods when the body repairs itself. In situ resource use changes the mass math. If a mission can extract water or hydrogen-bearing compounds, those stores become living shields that get better over time. Early architecture must still protect the crew before production ramps, so do not assume instant supplies. Plan for a first phase with launched mass, then a growth phase where local water, plastics, or regolith add layers. Printers and sintering tools that make brackets and blocks to hold that mass in place are small investments with large leverage.
Reliability and maintainability are part of protection. Radiation degrades plastics, cables, and coatings slowly. Build inspection into normal housekeeping. Swap panels that yellow or crack. Keep spares for the small parts that hold big pieces in place: buckles, straps, brackets, and seals. If a fastener fails during a storm drill, fix it same day.
The system must be robust to everyday bumps and to hurried movements when an alert sounds. EVA architecture is about limiting exposure while getting work done. Short, well-planned sorties from a bermed or lined airlock beat many small trips from a thin hatch. Rovers with water or polymer blocks behind seats shave dose while moving. Tool racks do the same. Fixed waypoints with shelter pods on long routes turn bad timing into a detour instead of a crisis. The fewer minutes spent standing still near thin hull or open terrain during active solar days, the better the lifetime dose curve looks. Logistics ties design to time. Resupply changes the shield. Each arrival brings full tanks and fresh pallets you can slide into protective stacks. Each departure removes mass you may have counted on. Architecture should treat cargo as part of the radiation system from the start. Cargo plans include not just what arrives, but where each item will sit to help protect crews until it is used. Human factors make safety automatic. People prefer light, open areas and views. Give them those, but put the long-duration seats and bunks behind mass. Place the nicest lighting and the most used screens where protection is thickest. If the safest spot is also the most comfortable, the crew will choose it without thinking. Design the shelter as a workable room, not a closet, so the decision to move during an alert is easy. Risk policy translates into numbers. Agencies allocate acceptable lifetime risk across missions and set per-mission limits. Architecture operationalizes those limits: aerial density around bunks, storm shelter thickness, maximum EVA time during elevated conditions, and required displays for dose rates and totals. The budget is visible, and the vehicle makes it easy to stay within it. In plain terms, good architecture spends mass-like money, heavily where it buys hours of protection for the brain, eyes, and marrow, lightly where nobody lingers. It turns necessities, water, food, waste, plastics, into walls that quietly work all day. It assumes the shield will move and makes moving it easy. It avoids exotic heroics and invests in comfort, drills, and maintenance so crews actually use the protection they have. That is how a mission remains both possible and safe enough to live with. Let's make this practical. If you had to fly tomorrow, what protection could you actually build, maintain, and rely on? Start with what already works. Hydrogen-rich materials are the backbone: water in flexible bladders, polymer panels, and boron-loaded liners. They slow and soften charged particles without producing the heavy showers of secondaries that dense metals make. Water earns a permanent place because you must carry it anyway. Wrap sleep stations and high-occupancy desks with water bags. Route potable and grey water tanks to form wet walls around torsos and heads. Turn waste streams into shielding by packaging urine, brines, and processed waste into sealed bricks that slide into racks around crew quarters. Polymers fill the gaps where plumbing is awkward. Panels of ultra-high molecular weight polyethylene become lockers, bunks, and cabinet backs that double as quiet shields all day. Where neutrons matter, add a thin boron-rich layer to catch the slow ones before they wander into living space. Think in layers, not slabs. A hydrogen-rich face where primaries arrive, a neutron-taming sheet behind it, and only the thinnest bit of metal where you need structure or mounting. You are shaping the spectrum on purpose. Gentle slowing first, clean up second, so you do not create a hard photon tail right next to people. A compact storm shelter is non-negotiable. Place it close to where the crew spends time so no one wastes minutes reaching it.
Build its walls from water, food, and polymer panels stacked to reach a healthy aerial density in the low double digits of grams per square centimeter. Put the thickest mass behind heads and chests. Strap every tank and pallet so nothing shifts when the hatch closes. Make the room comfortable enough for hours. Fans, lighting, CO2 scrubbing, a small console for comms and work. If the shelter is unpleasant, people will delay moving during a real event. Comfort turns into safety because it removes hesitation when the alarm sounds. Geometry is free performance. A uniform cocoon burns mass where you do not live. Instead, thicken the places you inhabit. Bunks, galley seating, planning consoles. Mount seats so torsos face polymer or water, not windows. Keep viewing windows small and give them internal roll-down bladders that can be filled with water during quiet periods and drained for photography or docking. Map dose rates by zone and rearrange mass until the hot spots cool. The kilograms you already carry will do more when they are in the right place. Operations bind the hardware into a system. Run with 3 modes: quiet, elevated, and storm. Quiet means normal work with baseline shielding. Elevated trims exposure, shorter EVAs, more time in thick zones, tighter monitoring. Storm is shelter, period. Drill sprints so the move is reflex. Keep rover routes and airlock staged to make retreats fast. Track personal dose with live displays. Green, yellow, red is better than a spreadsheet. If a workstation runs hot, move tanks and panels, not people, and confirm with new readings. The habit of small weekly adjustments keeps protection aligned with how the crew actually lives. On planetary surfaces, thickness becomes affordable through local materials. Berm or bury habitats under regolith to add large aerial density without launch penalties. Pair that soil outside with hydrogen-rich liners inside to clean up the spectrum that leaks through. Line airlock vestibules and frequently used corridors with water panels so routine passages shave rather than add dose. Outside, put polymer blocks or water behind rover seats and in tool caddies. The primary defense on EVA remains time and timing. Short, well-planned sorties during quiet conditions, never far from a shelter pod or a bermed outpost. Measurement closes the loop. Fixed sensors show dose rate in each zone. Personal dosimeters ride on the torso and, when possible, near the eye to track lens exposure. Weekly, compare maps to routines. Do people really sleep where the walls are thickest? Are they lingering near thin hull for a view? Small behavioral nudges and a few relocated tanks can shift the curve more than chasing a new material. That is the now. The near-term roadmap builds on it rather than replacing it. Expect better hydrogen-rich composites that hold shape, resist radiation embrittlement, and accept fire-safe skins without sacrificing the hydrogen core. Expect modular water bladders that plug together like bricks, with quick latches and drip-free coupling so you can reconfigure walls in minutes. Expect boron-loaded films and paints that add neutron control as a thin inner layer. Expect more capable inflatables whose internal webs accept polymer liners cleanly, turning soft volume into thick, quiet walls around bunks and labs. Resourcefulness will spread into manufacturing. Printers that turn packaging plastics and worn components into fresh shielding tiles are straightforward to field and maintain. On Mars, methane and oxygen production for fuel can feed plastic synthesis, turning local chemistry into panels and liners as the mission matures. Even simple cloth and polymer duffel shields that pack with food or gear and then mount as flexible pads will help keep geometry optimized as consumables ebb and flow. Forecasting and autonomy will sharpen. Onboard space weather packages tied to simple go-no-go thresholds will shorten the time from warning to action. Machine-readable alerts that drive lights and tones remove ambiguity. Crew do not debate, they move. After the event, logged dose rate curves show exactly how well the shelter performed, guiding small upgrades to panel stacks and tank placement. Active ideas, in the near term, find their niche as helpers. Localized magnetic loops can protect sensitive external instruments without bathing the cabin in flux.
Controlled electrostatic techniques can manage charging and reduce arcs, lowering indirect risk to electronics and optics. Laboratory work on plasma bubbles will continue. Any deployed system should be treated as a dose reducer for the lower energy tail of solar events, not as a force field. If it fails, the passive layers and the shelter must still carry the day. Medical support will stay conservative. Antioxidants and radioprotective agents may offer small benefits, but none erase the core problem of high Li-T tracks. The dependable tools are sleep hygiene, CO2 control, exercise, and nutrition that supports repair pathways. Crew selection and rotation manage lifetime dose. Personal budgets stay visible so ambition does not outrun margins. Surface living will get smarter with time. Early outposts rely on launched polymers and waterliners. Later, printed regolith blocks and sintered shells build berms higher and thicker. Habitats will migrate slightly or add modules to place sleeping quarters under the best cover. Windows will remain few and small, paired with cameras and displays that give views without exposure. The most used work surfaces and screens will naturally drift into the thickest parts of the interior, because that is where crews prefer to sit once comfort and lighting match. Cost discipline remains the gatekeeper. The winning ideas are the ones that do double duty. Water that cools a rack and shields a bunk. A locker wall that stores tools and softens the spectrum. A shelter that is also the planning room so people spend time in the safest spot even when the sun is quiet. Exotic materials that promise a few % improvement but demand special handling will lose to ordinary hydrogen-rich mass arranged with care. Put all of this together and the picture is clear. Today you can fly with hydrogen-rich walls where people live, a storm shelter built from the supplies you already need, disciplined operations that respond to weather in minutes, and a habit of moving mass to where it buys the most protection. Tomorrow, you can add better polymers, smarter modular bladders, simple in-mission manufacturing, and targeted active helpers. None of these steps create a perfect bubble. Together, they push the odds in your favor day after day without a miracle breakthrough. The result is not zero, but a level of risk the human body can live with for as long as the mission demands. There is no off switch for space radiation, and zero is not something you can buy with thicker metal, stronger magnets, or a miracle pill. The only strategy that holds up is a combined one. Soften the spectrum before it reaches people. Put real mass in the places where bodies actually spend time, and turn timing, routing, and disciplined habits into everyday protection. Hydrogen-rich matter anchors the plan because it slows charge particles without flooding the cabin with harmful secondaries. Dense metals stay in the toolbox for structure and special photon problems, not as the front line. Active fields help at the lower energy end during solar activity, but they are not force fields. Biology sets the ceiling, operations keep you below it. In practice, that means living behind water and polymers whenever you can. Bunks, galley seats, and work consoles sit inside wet walls and polymer panels with boron-rich liners to clean up neutrons. Windows are for planned moments, not background life. Internal bladders filled with water close them during routine hours. The interior is shaped so torsos rest behind the thickest, most helpful mass, and dose maps are checked often enough that hotspots get cooled by moving tanks and panels rather than by moving people. Daily rhythm turns into 3 clear modes. When forecasts are quiet, you work as planned with baseline shielding. When conditions are elevated, you shorten time outside, shift tasks into thicker zones, and watch dose rates more closely. When the storm alarm sounds, you do not debate. You move to the shelter and close the hatch within 90 seconds. That room is comfortable enough to stay for hours, with airflow, lighting, CO2 control, and comms, and its walls put low double-digit grams per square centimeter of hydrogen-rich mass behind heads and chests, so a dangerous spike becomes a survivable interruption. You leave when instruments say it is safe, not when hope says so.
outside the vehicle, timing and distance rule. You schedule EVAs only on quiet forecasts. You keep routes close to an airlock or a rover with shields behind the torso, and you set a hard stop by time or integrated dose. 5 more minutes is not a habit. It is a risk you do not take. Personal dose budgets stay visible, green, yellow, red, so ambition never outruns margins, and suit dosimeters fold into planning for the week ahead. On the surface, thickness becomes affordable by using local soil. Habitats are bermed or buried, then lined inside with water and polymers so the spectrum that leaks through is softened before it reaches people. Airlocks become short, shielded vestibules, and frequently used corridors carry water panels, so routine passages shave exposure rather than add to it. Out on the terrain, rovers and tool caddies carry polymer blocks or water behind the torso, and work remains short, planned, and close to a shelter pod or bermed outpost. Numbers keep everyone honest. Fixed sensors report zone dose rates. Personal dosimeters ride on the torso and, when possible, near the eye for lens tracking. Crews sleep where the numbers are lowest and shift mass when maps say they should. A simple weekly ritual maintains protection as supplies change. Full tanks move forward, waste is packed into sealed bricks that slide into the gaps food once occupied, and the storm shelter is checked to ensure it still meets its target thickness after every major resupply or consumption cycle. Targeted active systems earn a limited role. Localized coils or electrostatic techniques protect sensitive instruments and trim the lower energy charge tail during solar events with power, cooling, and failure modes planned in advance. Neutrons and photons still demand passive layers. Medical support stays practical. Sleep hygiene, CO2 control, exercise, and nutrition that favor repair pathways. No supplement erases high-let tracks, so the shield you build and the habits you keep do the real work. Success does not look dramatic. It looks like crews naturally spending most hours in thick, comfortable zones, like a shelter close at hand that people use without hesitation, like dose maps flattening month by month as mass follows habits, like EVAs that are short, quiet, and boring because they happen on the right days. The payoff is simple. Stop chasing a perfect bubble. You cannot build and stack small, reliable advantages, materials that soften, geometry that hides, schedules that dodge spikes, shelters that work, and numbers that drive decisions, until the risk curve bends enough that the mission is not only possible, but livable. Space will never grant us a perfect bubble. There is no switch to turn radiation off, and there is no single gadget that makes the danger vanish. What we can build is a livable margin. Hydrogen-rich walls where people actually sit and sleep. A shelter that turns a spike into an interruption. Routines that dodge the worst hours. And constant numbers on the screen to guide small adjustments. Layer by layer, habit by habit, the spectrum that reaches the body grows softer and rarer until missions stop feeling like bets and start feeling like work. That is the honest destination. Not zero, but control. Not bravado, but craft. With the materials we already carry and the discipline we can train, crews can travel and live beyond Earth while keeping risk inside human limits. Tomorrow we'll add better polymers, smarter modular water walls, cleaner forecasting, and targeted active helpers. But the physics will still reward the same moves you heard today. Soften, hide, time, and measure. If this helped you see the problem clearly, save the video, share it with someone who thinks more metal is the answer, and subscribe for the next chapters. If you want to go deeper right now, watch the episode on why we cannot start mass colonization of the moon yet, and the one on how a Carrington-level solar superstorm would stress modern civilization. I'll see you there.